The event, S250206DM, a ripple through spacetime. On February 6, 2025, a subtle but unmistakable ripple traveled across the universe and brushed past Earth. It was caught by the ultra-sensitive detectors of LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo, which had just resumed operations after another round of calibrations and upgrades. The signal, designated S250206DM, bore the cosmic fingerprint of a truly cataclysmic event, something so massive, so violent, and so far away that its effects could still be felt here in the form of infinitesimal distortions in the very fabric of spacetime. This event, though still shrouded in mystery, may turn out to be one of the most remarkable detections in the history of multi-messenger astronomy, a discipline that synthesizes data from gravitational waves, electromagnetic radiation, light, and particles like neutrinos to piece together cosmic events with unprecedented clarity. What are gravitational waves, and why do they matter? To understand the significance of this detection, we must first grasp what gravitational waves are. Gravitational waves are ripples in space-time itself, traveling outward from massive accelerating bodies, particularly those undergoing sudden changes in motion, like colliding black holes, neutron stars, or even hypothetical phenomena like cosmic string interactions. These waves were predicted by Albert Einstein in 1916 as a natural consequence of his general theory of relativity, but he himself doubted they would ever be detected due to their minuscule effect on physical matter. Yet, they are profoundly important. Unlike electromagnetic radiation, which can be absorbed or scattered by matter, gravitational waves travel virtually unimpeded across billions of light years, carrying pure, unfiltered information about their origins. They are messengers from the deepest corners and earliest moments of the cosmos. The first direct detection of gravitational waves in September 2015, GW 150914, was a watershed moment in physics. It confirmed a century-old prediction, opened a new window to the universe, and awarded the Nobel Prize in Physics to key contributors. The signal came from the merger of two black holes, each several times the mass of our Sun, and traveling toward each other at half the speed of light in their final death spiral. Since then, LIGO, Virgo, and later KAGRA, in Japan, have detected dozens of such events, painting a richer, more chaotic portrait of our universe's invisible dance of death among massive bodies. The anatomy of a detection, how we capture ripples in spacetime. Gravitational wave detectors, like LIGO, are marvels of precision engineering. They function as Michelson interferometers, two perpendicular arms stretching 4 kilometers in length, with laser beams bouncing between mirrors at either end. Under normal circumstances, these beams recombine perfectly. But when a gravitational wave passes through Earth, it slightly stretches one arm and compresses the other, changing the timing of the laser paths by a distance less than the width of a proton, yet enough to generate a measurable signal. These distortions are so minute that LIGO's sensitivity is equivalent to detecting a change in distance between Earth and Alpha Centauri to within the width of a human hair. What makes S250206DM special? Now back to the new detection, S250206DM***. What sets this event apart is not merely that it occurred, but how it occurred, and what it might represent. Several features of this detection have experts buzzing. 1. Unusual signal characteristics. The waveform's frequency, amplitude, and duration suggest that the event may have involved non-standard compact objects, perhaps an unusually massive neutron star, or even an exotic hybrid such as a boson star, quark star, or a primordial black hole. 2. Neutrino coincidence. Almost immediately following the gravitational wave detection, the IceCube Neutrino Observatory at the South Pole registered the arrival of 2 high-energy neutrinos. The statistical likelihood of this being a coincidence is just 0.1%, hinting strongly at a multi-messenger event, where gravitational waves and particle radiation are emitted from the same cosmic source. 3. Still searching for light. Unlike some previous detections, such as the spectacular GW 170817 neutron star merger, no electromagnetic counterpart, like gamma rays or visible light, has been found Asterisk, asterisk, yet asterisk, asterisk. But telescopes across the globe are now scouring the region of the sky indicated by the gravitational wave data to find the flash of light that would confirm the identity of the progenitor event. Gravitational waves plus neutrinos, a potential triple discovery. If astronomers eventually detect electromagnetic radiation linked to S250206 light across any part of the spectrum, it would be the first confirmed instance in human history of a triple messenger cosmic event, where all three fundamental carriers of astronomical information, gravitational waves, light, and neutrinos, were observed from a single astrophysical occurrence. This would be monumental. It would sharply constrain the nature of the source, e.g. neutron-star merger, exotic black hole-neutron-star interaction, or even something truly novel. Illuminate the dynamics of relativistic jets, matter ejection, and nuclear synthesis in the aftermath. Provide new insights into neutrino physics, including their mass, interaction cross-sections, and production environments. The future of detection. LISA and the new generation of observatories. While ground-based detectors like LIGO and Virgo are powerful, they are limited by seismic noise and Earth's finite size. To reach lower frequencies and detect supermassive black hole mergers, we'll need to go to space. Enter LISA Laser Interferometer Space Antenna, planned for launch around 2035. It will consist of 3 spacecraft flying in a triangular formation 2.5 million kilometers apart, creating an interferometer in space. LISA will be able to detect gravitational waves from sources billions of times more massive than those detectable on Earth, probing the early formation of galaxies, black hole mergers in the hearts of quasars, and potentially even cosmic inflation itself. Why this matters for humanity. The study of gravitational waves is not just a technical curiosity. It's a transformational leap in our ability to perceive reality. Think of it like this. Before 2015, we were effectively deaf to the universe. We could see stars, galaxies, nebulae, but we couldn't hear the cosmic symphony. Now, with every detection, we're not just looking at the stars. We're listening to their final screams, collisions, and triumphs. We are, for the first time, becoming fully aware of the dynamic, cataclysmic, and astonishingly active nature of the cosmos. And with each signal, like S250206 we're getting closer to answering fundamental questions. What happens at the edge of a black hole? How did the first massive stars die? Are there exotic forms of matter beyond our current models? Could we eventually detect echoes of a previous universe, or even evidence of a multiverse? In conclusion, a new dawn in cosmic storytelling. S250206 may not yet be fully understood, but it's another step toward mastering a new language. Asterisk the language of space-time itself star. A language that reveals truths too deep for light to carry and too ancient for matter to preserve. As we analyze the data, search the skies, and refine our models, we may soon unlock a mystery that forever changes our understanding of how the universe lives, breathes, and dies. So keep watching the stars and listening. The universe is speaking in waves.